Okay, cool. So once again, welcome to this workshop being hosted by Quantum Computing at Davis. Historically, I think in the last two workshops, I took a look at the quantum Fourier transform, which is an integral part of many quantum algorithms. But today, I think I wanted to kind of step away from all the math and the algorithms and really look under the hood. Most of the time, when people learn quantum computing, especially for the first time, the priority has always been more on algorithms rather than the underlying hardware. But I think it's still very prudent to take a look at that hardware. It gives you an idea of how exactly things work, and it might help your understanding about, okay, what exactly is behind each of these wonderful little squares that may represent certain unitary operations on your circuit. So with that being said, I'm going to go ahead and share my screen here. I have OneNote open, awesome. And hold on, let me arrange things here. If any of you have questions, feel free to interrupt, unmute yourself, or you can go and chat. I'm trying to get that open right now. Okay, cool. And I'm more than willing to stop, and I'll be able to answer any questions that you may have. So with that being said, I want to kind of preface this by saying that most quantum computers have different kinds of qubits. So the qubit is just short for quantum bit. And it is a sort of fundamental unit of quantum computation, just as how the computer or cell phone you're watching this thing on right now may use a singular bit, that represents a 1 or a 0. The quantum bit, represents kind of the superposition, and you can do entanglement and all your fundamental operations that way. But what exactly constitutes a qubit can actually vary tremendously. There isn't really a restriction on how a qubit works. The only thing a qubit really needs to be able to do is be able to represent some kind of quantum superposition. So, ket psi, and then you have some combination of ket 1 and ket 0. So these sort of two orthogonal basis states in a sense. And you can construct any superposition of those states that you'd like, or you should be able to do entanglement as well. But this definition leaves a lot of room for what the hardware might look like. And today I want to take a look at one form of that hardware, and that's known as sort of the Ion Trapped Qubit. Ion Trapped Qubit. And the name is pretty self-explanatory. Yes, we get some ions and we trap them. But I really want to kind of dig into how it is that you can take these ions and perform useful quantum computations with them. And before I jump into that, I want you guys to keep this in the back of your mind while I'm sort of going through the myriad of steps required in order to pull off this useful computation using certain atomic ions. And it's something known as DiVincenzo's criteria. If you look up DiVincenzo, you will find a basketball player. So if you really want to read the original paper, please write out the full thing. This is known as DiVincenzo's criteria. There are 7 criteria, but 2 of them are related to quantum communication. So if I had 2 quantum computers and I wanted them to talk, or if I had a quantum computer, excuse me. If I had, there we go, let's fix that. If I had quantum computer 1 and I wanted to, transmit some information to quantum computer 2, there would have to be some kind of quantum channel or some way to transmit these qubits. So those are the last 2 criteria. But I want to focus on sort of the first 5 criteria of DiVincenzo's. And these criteria are sort of the golden standard for what a usable quantum computer should look like. So if you or anyone comes up with a model for a quantum computer, it better be able to satisfy these criteria. And right now we're at a point where it seems like most qubits can satisfy these criteria, but there are 1 or 2 sticking points that you can still satisfy the criteria, but it's by no means an ideal scenario. So your first criteria is you want a scalable system with a well-characterized qubit. So I'll just start with 1. So that means that my system can either it can either have a singular qubit. Hold on, yeah, let's go ahead. Singular qubit. It can have a singular qubit, or it can have any number of qubits. So I can have a great deal more qubits, and I should still be able to hold things together. And a well-defined qubit essentially just means it pretty much satisfies this definition that I gave above here. You have your two states, and then you can have some kind of superposition of those states. And trapped ions do this pretty well, but I want to put a little asterisk here because the scalability is something that gets particularly tricky when it comes to this particular mode of computation. We also want the ability to initialize a state of qubits into a simple fiducial state. Don't worry too much about the definition of fiduciary or fiducial is. It just means like when I start my computation, I should have a very well-defined beginning state. And in this case, in literally every quantum simulator or computer, we always like to start out, with some number of, this tensor space of, all these zero states essentially, or ket zeros. So we have to be able to get all of our qubits to start off in this very well-defined state. And then let's see, our third property of long relevant decoherence times. So decoherence is it's one of the biggest problems with quantum computing. It's if you have some kind of superposition state. So if I had my, oh, whoops, that's a terrible circle. If I had some kind of superposition state, I want to be able to stay in this quantum state. So it could be a traditional superposition like this. Or it could be anything else on the block sphere. But regardless, I should be able to stay in this state long enough to perform useful computations. Decoherence is just when your quantum state collapses and you lose this superposition state or any quantum properties, and then eventually you find out like your result is total gibberish because you are not working anymore in a quantum state. So we should be able to stay in this quantum state for very long periods of time, or at the very least, long enough to perform useful operations. So like, I could put a Hadamard here. Maybe there's some rotation along the y-axis, and any number of these. And the time that this thing lives should be able to exceed the time of these operations. So it might be friendlier to define this in relative terms, like the gate time versus the time the qubit lasts versus any specific amount of time, say 1 millisecond or 10 seconds. And then let's see, we have two more properties here. I'm going to go ahead and skim over them very quickly, number 4 and 5 here. Universal set of quantum gates. So what this means is that most algorithms, especially research papers you'll find, have quantum algorithms that are defined as a series of sort of different standardized gates, like Hadamard, or maybe this X gate, or you could have a pi/4 rotation, and then you can have all kinds of stuff. But the reality is most hardware systems, like the actual hardware doesn't really understand. There's no native hardware implementation of a Hadamard or an X gate. What actually happens is you have to sort of rely on the compiler to break down these gates into a sequence of other gates. Perhaps you have a number of rotations or some other different operations, and this will represent one Hadamard. So to be able to have a usable quantum computer, I should be able to take any gate which represents any manipulation of our quantum state on this block sphere, and I should be able to break it down to a certain number of basis gates that will let me achieve any kind of configuration that I want to. But usually for a universal gate set, you need maybe you'll need one single qubit gate, and then you'll need one double qubit gate. So like this single qubit gate could represent any arbitrary rotation you want, and then you'll also need this gate here. Which will, usually it's like a C0. It doesn't have to be a C0 though. It could be a controlled phase gate, but you'll need some kind of a rotation gate, and then maybe this thing that will couple two different qubits together. So this is qubit A and qubit B. So it allows for this interfacing to go on, and this would become your universal gate set, because just with these, with a smaller set, you can express any other algorithm or circuit you have in mind using these two gates. So a quantum system needs to have some combination of these gates. And then our last criteria here is a qubit-specific measurement capability. So what that means is, if I am in some kind of quantum state, let's say we don't know what this is, right? We'll just say this is psi. I should be able to perform some measurement on this thing. So if I wanted to measure against a certain state here, you can just express it this way in bracket notation. But usually it just means like, okay, if you are in I always like the visual route. Makes things a lot easier to work with here. If you're in some quantum state like this one, and then you perform the measurement, should be able to tell, okay, am I does it go to Ket 0 or Ket 1? And this should be very well defined. You should not have, I shouldn't have the problem where I run this maybe like 50 times and your answer is still like, there's some kind of margin of error. That would be very unacceptable for a quantum system. So you should have a very well-defined ability to perform this measurement. And you will find out soon enough that your ion trapped qubit actually hits all of these perfectly. It is very capable of hitting all these criteria. Although, don't forget this asterisk I put here. Near the end of today's lesson, you will find out very quickly why this is such a problematic thing, scaling up the number of qubits in an ion trap system. So these are sort of DiVincenzo's criteria. I want you guys to keep this in the back of your mind. Because as I kind of hit each point of how the system works, you'll realize like, oh, it does have all the criteria kind of ready to go in a sense. So it has a very nice property like that. Now, with that being said, let's actually get into talking about these ions. And after all, I mean, it is in the name. So, all right, so here we go. I want to first start off by talking about the energy levels inside atoms. So we know, traditionally the traditional picture is like, oh, you have some kind of a nucleus here. I actually can ignore this large charge. I'll save myself some time here. There's a large nucleus, and it has like a number of electrons that are orbiting it. And this is sort of the Bohr model with, these sort of concentric circles and everything's all nicely spaced. But this is not an actually accurate reflection of what's going on here. Reality, if I were to look, this atom has its own sort of different energy levels. So I don't know if any of you have taken like high school level chemistry or undergraduate level chemistry, you're very familiar with these and the idea of orbitals, mainly that the electrons don't orbit the nucleus, but they exist in these very interesting and wonderful looking electron clouds that seem to surround the nucleus. And then I won't even try drawing, oh, this is P, that's D, and then an F orbital, things start to get a little hairy. But basically, to describe the energy levels inside an atom, and these energy levels, mind you, are where electrons exist. So electrons can occupy different energy levels inside your atom. And normally, you can usually have like a nice little chart that looks like this. It'll show like your energy, and then you would have, a different number corresponding to like the number of suborbitals that your electrons can occupy and whatnot. But let me get into a little more detail here. This is a little sloppy. I'm just trying to give you guys sort of a visual representation of what is going on here. So if I give you an electron, and the electron is somewhere inside this massive atom, and I would ask you, okay, I want you to uniquely identify that electron in your atom. The way you have to go about doing that is we use what are called quantum numbers. Quantum numbers are a natural result of solving Schrodinger's equation for different different setups or configurations. And for the atom, there's sort of 4 quantum numbers that you'll need to know to identify a particular electron. You'll need N, L, M sub L, and then M sub S. So this is your principal energy level. L is going to be your, let's see here, quantum orbitals. Oh, so L kind of defines the orientation of your, or no, that's oh, L is the shape of the orbital. Excuse me. Wow, it's been a while since I took chemistry here. L is sort of the shape of the orbital. So all these fun little configurations that I've drawn here, like this double lobe or this quadruple lobe. M sub L is the orientation. So if you notice that, like for this p orbital here, the p orbital could be sitting along the z-axis, or it could be along the y-axis or the x-axis. So this number kind of defines the orientation. And M sub S is the spin. So for electrons, you can either have electrons in spin up, or they can be in spin down. So these are sort of your 4 quantum numbers, and these help kind of characterize individual electrons inside your atom. Now, I had this diagram up here earlier with the different energy levels. I'll go ahead and, but I'll just oversimplify this thing. But inside your atom, you can have, let me draw E here. You can have these different energy levels. Electrons can exist in different levels, and there are different occupation rules, like how many electrons each level can occupy, so on and so forth. But the basic idea is that we can take we can pick two of these energy levels. We pick two of these energy levels, and we can treat them as kind of the orthogonal vectors that I drew when I was drawing like the arbitrary qubit state. So you have some mixture of this vector and some mixture of that vector. All you really need are two kind of eigenstates, and you take the superposition or some superposition between those states. So in this case, I could easily say, okay, for this low energy or ground state, this is ket 0, and for this a higher level energy, it's ket 1. So we can use the energy levels inside an atom to create our qubit. And I'm kind of getting towards why we need an ion configuration and all that stuff. But this is where I want to make a very clear distinction with you all, because when I say ion trapped, they're actually two different kinds of ion trapped qubits. In fact, the total is 3. For the purposes of brevity, I'm omitting the third kind, although if you're interested, you can look up a Zeeman qubit. That's Zeeman with 2 E's. So there's the optical qubit, optical, and then we have hyperfine, optical and hyperfine qubits. These are both ion trapped qubits, but the way you pick the energy levels are remarkably, there is a significant difference to these. So with the optical qubit, actually, hold on. I digress here. I should have also mentioned something else. I just realized this is something that should have been right after the stuff I said here. So keep that thought in your mind. There are 2 different kinds of qubits. But the basic idea here now is you can promote or demote electrons. So if I have an electron kind of sitting here at the sort of ground state, and this is the excited state, I can make this electron kind of go up. I can make it jump. I can give it some energy, and it will go up to E, and then it can also release radiation and go down to G. But we know because this is a quantum system, your energy levels are quantized. So if I give this photon, or this electron, we're still in the ground state. If I give the electron a little bit of energy, it's not going to, it can't stay in that level forever. This is a sort of forbidden state. So as a result, it's just going to stay here in G. So if I were to shoot my photon at it, this is a photon. And remember, the energy of photons is defined by this formula here, Planck's constant times the frequency of your photon. And it is not representative of this sort of energy level. That electron's not going to do anything. It's not going to budge. But with the right, once I get this photon to the right frequency, I can promote that electron. So the electron will go ahead and happily jump up to this other energy level. And you can also have spontaneous decay, where it will, or spontaneous emission, sorry, not spontaneous decay. Spontaneous emission is just where eventually it can't stay in the excited state forever, and eventually it will fall back down and it will emit a photon that also obeys this property here. So as a result, we can, if I have this kind of electron kind of sitting here, as a result, I can toggle it back and forth using a specialized photon configuration, aka a laser, and I can represent superpositions and my manipulations. Although I say laser like it's it's a very trivial thing to just we just shoot some photons and toggle between these states. In reality, it's an incredibly nuanced procedure. In fact, I want you to this particular configuration. I'm putting an asterisk here as well, because there is something called a Raman transition, or a stimulated Raman transition, where this is actually possible, but it's not something to be trivially explained. What I can explain at best is probably going to be very superficial. But keep this in mind. Keep this in mind. That is a pretty key to how this operates. Now, there's also something else that I didn't mention here. I've sort of mentioned, like, okay, so if we use SP, D, and F, or not S, N, L, M sub L, and M sub S, are 4 quantum numbers, and I can tell you where any electron is in all these different energy levels. So this n equals 1, and then you could have n equals 2, and then you might have n equals 3, or some configuration here. There's something called a hyperfine splitting, or it's called hyperfine splitting, or the hyperfine structure. I like the term hyperfine structure just because it sounds cooler. But the basic idea behind the hyperfine structure is, if I look at some of these energy levels, right? So if my electron is just sitting at, say, the principal energy level is 2, and it might be sitting in a p orbital, or maybe even a higher configuration, what happens is this electron has spin, and as a result, it has its own kind of magnetic field towards it, or a magnetic moment. But we have to remember that the nucleus of our atom, so if this was the nucleus, then you have your electrons just happily orbiting around it. The nucleus also exhibits a kind of magnetic moment as well. And as a result, the electron and the nucleus, when they start interacting with each other, what happens is your singular energy levels can actually split. It's an incredibly narrow split in terms of energy levels, but it can actually happen. And if you're really curious about the exact details about what's going on here, I highly recommend the Feynman lectures. So if you look up Hyperfine Structure, Feynman lectures, Feynman does an absolutely beautiful job of explaining what's going on here. And one example that I can give, and he gives a, this is pretty much, I'm directly quoting from Feynman here, is if we imagine a hydrogen atom. So, hydrogen's one of the simplest atoms in existence. We just have one happy proton and one happy electron, and they're orbiting each other nicely. Hydrogen does have a ground state, but Feynman points out there are actually 4 different configurations for this ground state. This can actually split up into 4 other sub ground states, if you will, because the proton can also be spin up or spin down, and the electron can also be spin up or spin down. So as a result, you can get, assuming that this is the proton and this is the electron, you could have both of them be spin up. You could have spin up and spin down. You could also have spin down, or you can have it the other way around, where the proton is spin down and the electron is spin up. So this results in what we call the hyperfine structure, where you can have a singular energy level that actually splits up into multiple smaller energy levels. And now, I jumped the gun earlier, but now I bring this back. We can have your sort of hyperfine qubits or optical qubits. And now this should start to make sense here. Both are ion trapped. With hyperfine qubits, what happens is, if this was like a singular energy level, sort of an S orbital, with the hyperfine structure, I define my ket 0 and ket 1 to be the hyperfine split between S. So I might have the electron could be here or could be here within the split energy levels. This could be this is just P. This is just a higher energy level that these guys can go to, and this will become important later on when we define qubit measurement. The optical qubit, on the other hand, is where you define your transitions to be whole energy levels. So as a result, I might decide to define my qubit to instead be, okay, this could be S, D, and then I would instead define this to be ket 0 and this to be ket 1. So you notice that these are whole energy levels. I'm not actually using the hyperfine structure in between them. And the reason why they're called optical is because the amount of energy or the frequency that I need to toggle the electron to go from 0 to 1 and 1 to 0 is in the optical range. It's something that our eyes can see. So this is sort of your optical qubit. And whereas, in hyperfine, if I'm talking about like a ytterbium atom, I think if I remember this correctly from the top of my head, ytterbium 117 with 1 electron missing. And this is actually improper notation here. It should be plus and then be 117 there. If I was using a ytterbium atom, the energy required to go from 0 to 1 is in the microwave regime. So this is about 10 to the 10 hertz, or it's in the microwave region. So these are your 2 options for ion trapped qubits. And for the sake of this explanation, just because it seems the great majority of friendly resources focus around the hyperfine qubit, I will continue my explanation using the hyperfine qubit. And the hyperfine qubit actually has a number of really nice properties. It's super long-lived. I'm talking, you can go from minutes to hours. Even from what I've heard, even days are possible. So you can maintain some kind of quantum state that way. Whereas optical is, I think, it's slightly shorter-lived, and there are problems with getting a laser that is tuned well enough to pull this stuff off. Although it does have its advantages as well. So there are disadvantages and advantages to both. But for the sake of simplicity, and what I think most people are doing these days, they focus on the hyperfine qubit here. Now, so I've sort of defined the 2 kinds of qubits. Before I go any further, are there any questions? Feel free to unmute yourself or put your questions in chat, because I'm more than willing to. I don't want this to be wholly one-sided. I do very much encourage people to ask questions if you have any, and I assume some level of knowledge with these workshops, but if there's something that really goes over your head, please don't hesitate to go ahead and speak up. I mean, that's my whole job here as workshop director.
Sorry if you already mentioned this, but I was wondering, how do you prevent, since we're choosing like two of these, I guess, energy levels to determine our two-level system, how do we prevent it from going into another energy level?
Okay. So this is that's an excellent point. In fact, it'll probably get brought up several times as I keep my explanation going. But it has to do with the quantization that I mentioned. So if I were to give some energy, so yes, this electron could go here and only here. In fact, there are certain rules that I omitted this from my explanation, but there's something called the selection rules. And the selection rules actually explicitly define which transitions are permitted. So there are certain transitions the electrons just simply cannot go to because the laws of physics don't permit it. Also, because these energy levels are quantized, I can give you a scenario here. Let's imagine you have some kind of three-level system, and I give some energy, so the electron will go to this energy level here. If I give a little more energy than that's, like if the frequency is off by maybe like just 1 hertz, why not? That electron will not, the transition simply won't even occur because it has to be a quantized amount of energy. It's got to be that specific number. You can't have like a variable amount of energy going to and fro. Does that does that answer your question, or is that kind of sloppy? Like, is there a
No, that makes sense. That makes sense.
Okay, cool.
Thank you.
Cool. Yeah, no problem. Feel free to go ahead and if there are any further questions. But that is a good point, though. You have to remember that these are quantized energy levels, so there are transitions that are permitted and not permitted as well, both for exciting and for energy decay as well. These are called selection rules. You can look them up yourself. I purposely am not writing them in because my explanation doesn't really require too much of this stuff here. But for to be thorough, it would definitely behoove you. All right. Well, it looks like I think everyone's happy. I see the number of participants is still staying at a healthy 7, which is good, because usually if someone leaves during the middle of a workshop, then that's sort of the red flag to me that maybe I'm really starting to lose my train of thought here. So with that being said, now I mentioned ions, but of course, ions have to be associated with some kind of element. And basically, the content from here comes from a lot of talks from Christopher Monroe. You're free to look him up on YouTube. Christopher Monroe has talked at many places. I think he talked at Stanford and or it might have been Harvard, Google. He's sort of like a premier expert. I would call him a premier expert on ion trapping. A lot of, I sort of cite some of his sources here. But now we get to pick which kind of ions we want to use. Because you have the whole periodic table at our disposal, right? I didn't really impose any other requirements, so there must be some. We're not using every single atom in existence to do ion trapped computing. That's for a very good reason. So usually the atoms that we're really interested in, I already kind of mentioned one of them. It's ytterbium. Ytterbium is kind of sitting down here. Or we could have the alkaline earth metals. So the alkaline earth metals would include beryllium, magnesium, and everything else down this column here. So you could have beryllium or magnesium, ytterbium here, and you could also have some of the elements here, or some of the metals, I should say. So these would include zinc, cadmium, mercury, your heavy metals essentially. So why is it that these atoms have kind of come to the forefront of attention for most quantum computing purposes? Well, it's because the electron configuration, the energy levels, are just really nice to work with. In particular, if you go to the atoms in this second column here, the outermost, or sort of your highest energy levels, have 2 electrons. So there's sort of like an s orbital at the. So if I were to like draw out the whole energy level, you go to the very top. There is an s orbital, and that s orbital has 2 happy electrons in a spin up and spin down. And if you ionize these atoms, you can strip one of these electrons out, and now you have it has sort of a very nice configuration as well. you can strip the electron. Excuse me, sorry, my train of thought just totally derailed for a second. Beryllium, magnesium, and then you can also have your heavy metals also have the same thing. They have 2 electrons at their highest energy level, and ytterbium also has 2 electrons at its highest energy level. So what exactly is the deal breaker, for these kind of 3 groups that we're dealing with? What is the breaking criteria here? Well, there are 2 criteria that you really want to pay attention to when you're picking out your ion or your atom for ion trap computation. The first one has to do with the frequency of light, or frequency or wavelength. I mean, they're both related to each other, that you're comfortable with working with. So the alkali earth metals are really nice because they like green light. So alkali earths, hold on, sorry, I should mention this here. The alkali earths, alkali E's, they work very well with green light. And this light, mind you, is responsible for doing all these wonderful optical manipulations between 0 and 1, and doing a lot of the rotations and stuff you might be interested in. Well, I say rotations, but I'll have to double check on that one. But basically, there's sort of like a main wavelength of light that you're working with to manipulate these qubits. So the alkali earth metals like green light. The heavy metals are kind of problematic. So your heavy metals, the ones that I just mentioned, zinc, cadmium, mercury, or more so cadmium and mercury, they like UV light, and not just like deep UV. And the chief complaint with using deep ultraviolet light is that most of the time when you're dealing with lasers, there's a lot of fiber optics, and UV light is not very friendly to work with in fiber optic setups. In fact, it can damage certain fiber optic setups. So that leaves friendly ytterbium here, and ytterbium works near UV. So we're working with near UV light here, and ytterbium is at least what Christopher Monroe is working with with ytterbium. And a lot of online resources may show ytterbium, but you might see calcium and other things as well. So your first criteria, of course, is, okay, what kind of light can I use? Do I have the equipment to manipulate the atom with that wavelength of light? But your other criteria is actually the mass of your atom. How big is the ion going to be? Because you notice that in the name, trapped ion, we do have to confine these ions. And you will be, there's a bit of jostling that goes around when you're manipulating these atoms. And as a result, ytterbium, being all the way down here on the periodic table, should be indicative of how big it is. It's a pretty heavy atom. It's got a lot of inertia to it, which may mean, you might have to exert a little more energy to kind of keep it within your trap. And, it might be nicer to work with some of the alkali earth metals. But at the same time, it's sort of a trade-off between the two. So there's kind of like the inertia, I would say, or the your mass. So those are the 2 criteria. And you might find older papers that even use aluminum as an atom for ion traps. And all the research is kind of strewn all over the place. I think even IonQ is like one of the companies that works with ion trap computers. They prefer calcium. Oxford also uses calcium as well. And you will, but basically you'll see a certain selection of atoms that are used frequently for ion traps, and your main reasons are, okay, maybe the frequency of light is very friendly to work with, the mass might not be too prohibitive, and yeah, oh, and the I guess the third one is like it should have a nice energy configuration. So all those energy levels, including the hyperfine structure, should be really nice for you to work with. So those are kind of your 3 criteria there. Now that we've kind of we've gone through all this kind of mess to explain atoms and ions, now we actually get down to the real computation. Now I'm actually going to show you all the moving bits and pieces that you require to get a feasible computation to come out of this whole setup. And once again, any questions, feel free to unmute yourself, interrupt, or drop it in chat. I have the chat window on my second monitor here, so I am actively monitoring that situation. All right, let's see here. So how do we go about making our ions? You have like a number of choices at hand, but the most common way to sort of make your ions usually is, the ions could be in some kind of solid form. You can literally heat them. So if you apply some heat, you get them into kind of this gaseous state. So you have like a nice cloud of, in this case, these would be calcium ions. If you go to the Oxford quantum computing, they use calcium as well. So they heat calcium to 800 degrees Celsius, and you have a nice cloud. And then you shoot, or you bombard this cloud with a bunch of high energy electrons. And as a result, these electrons will actually knock out the other electrons in the calcium. So you go from a normal sort of non-charged calcium to your calcium ion, which is great. But we still have a problem here. Your calcium ions are jumping all over the place like crazy. I mean, it's in this gaseous form, which isn't the main problem so much as the fact that it's just, it's a gas. I mean, it's going all over the place. You have to confine your ions somehow. And this is where we get to the actual trap mechanism itself. It's trapping. Usually, it's sometimes called an RF, radio frequency trap, or a Paul trap after its inventor, or not so much the inventor, but the person who figured out the principles behind how to trap things. Now, I want to briefly mention something. I'm not going to show you the math for this, but there's something called Earnshaw's theorem. And I just want you to keep that tucked away in your mind. For those of you that are more mathematically inclined, I strongly encourage you to check this theorem out. But Earnshaw's theorem basically states that we cannot use static charges to confine a charge in three-dimensional space. So what that means is, if I have this little charged particle, maybe it has like some negative or negative or positive charge, I can't just figure out some weird geometrical configuration that doesn't, like these, like let's imagine, these are static charges, static, and this is static, and maybe this is static, and then maybe I put like on like the z-axis, these are static electric potentials. So maybe it's all positive, and that is also positive as well. And naively we would think, okay, this should be able to make that ion not move. But the reality is this is forbidden. It doesn't work, in fact. So the workaround to this, so yeah, that's Earnshaw's theorem in essence. Earnshaw says that this configuration is not possible. You cannot just have static charges and keep your ions happy. So as a result, our workaround is we create what I call a, it's a dynamic potential, or you can even look up what's called a horsey. Why did I call it a saddle potential? Sorry, I was about to call this a horse seat, which isn't wrong, but it's more well known as a saddle potential. And the basic idea here is, okay, if we can't have a static potential, what we're going to do is, with some special configuration of electric charges, I can make this electric potential look kind of like a horse saddle. These would be more pronounced upwards. And then by fluctuating along a certain radio frequency, by fluctuating these charges, I can make this potential kind of rotate. So imagine a horse saddle or a Pringles chip, if you have any chips laying around, and you just continuously rotate that potential. And your ion is sitting at the very center of that horse saddle. So if it wasn't moving, of course, the electron might decide to fall off, or it might, kind of meander away. But if I keep rotating it, what actually happens is it creates this kind of harmonic potential here, this harmonic well. And as a result, your ion stays nice and comfy inside of it. And to give you a visual representation of what this looks like, you can imagine 4 rods, and this is literally what it looks like, 4 rods, and they're kind of in this square configuration. I really wish I could draw that other rod here. This is, wow, okay, yeah. So you have 4 rods going here. 2 of these rods are going to be tied to some kind of they're going to be grounded, so they'll have like some constant, or they might not even have any charge on them at all. But the other 2 rods experience a oscillating radio frequency, and as a result, when we take those gaseous ions, they're more than willing to kind of go single file. So the ions will line themselves up single file inside of our trap. And just to make sure, you'll notice that we constrain it on the x and y axis, but the z-axis, all we're doing, the z-axis, actually we cap it off. So there are 2. You're going to have 2 static charges here, so like a constant positive charge, to prevent these ions from just popping right out of the potential. So as a result, we now have our ions are now confined. This is a Paul trap, and you'll notice if you look at a picture of like what IonQ does, you have the chip here, and you'll see something that looks like this. It looks kind of like a Y. And this still follows the same principle, but the structuring is slightly different. In fact, if you look at older research papers, the Paul trap, this is a linear trap. Other times, if you have a smaller number of ions, you're not doing quantum computation, they'll do this weird hyperbolic node where it's like you have like your 2, and then you have this weird central electrodes. So it's sort of like one, 3 electrodes. But this is just a side note. But basically, for my explanation, I like the Paul trap better because it's easier to see why it is your ions line up nice and tidy, or in this nice little a single file line. So now we're ready to do computation, right? Well, no. Because your ions still have some kinetic energy. They're still kind of moving about to and fro. They still have some associated temperature to them. And we need a way to kind of cool them down. And this is where I'm going to introduce the concept of Doppler cooling to you guys. Once again, if there are any questions about this trapping, feel free to go ahead and ask in chat, because this is, but basically now we want to try and cool down or reduce the kinetic energy of our ions. And we use Doppler cooling. So what is Doppler cooling? Well, it has to start off, it starts with a very counterintuitive idea that by using a laser, I can somehow cool down, a material. And this seems like very antithetical to what you might already know, or you intuitively may know, because energy lasers can also very well heat things up. But the way we're using the laser is to cool these things down, and it has to do something with what I mentioned earlier. So if you imagine a moving atom, so this atom is moving, it has some velocity, and it's moving, and what happens is I'm going to shoot a photon into this atom. Now, what happens is photons don't have mass, but they do have momentum. So as a result, the atom will go into this kind of excited, it goes into an excited energy level, and it will later on, so this is sort of phase 1, and then phase 2, later it will it undergoes spontaneous emission. So then that photon gets radiated outwards in a totally random direction. But the basic idea here is that using the momentum of this photon, which the atom is happy to absorb and reemit, I can start to slow down. The atom here. And if you remember the definition of temperature, right? Temperature is sort of the average kinetic energy of your particles, right? So if I reduce the velocity of all these jostling atoms, then I can reduce the temperature as well. And once again, average here is important, because if you know the Boltzmann distribution, in a gas, your particles are not really, they're not all moving, at the same energy at the same speed. It kind of follows this, it follows a kind of distribution here, or a Boltzmann distribution. It should be called I think it's called the Boltzmann-Maxwell distribution, to be thorough. But there's still a problem here. Let's say that I've slowed the atom down, but if I keep shooting photons into the atom, I could very well inadvertently speed up the velocity again in the opposite direction, in which case I increase the temperature. So we have this kind of problem here, where we need to be able to get the atoms to, we only want the atom to absorb the photon if the velocity is in our direction. This is the only thing we want. We only want, if the atom is moving away from the laser beam or the photon, we don't care anymore. And this is where the Doppler effect comes in handy. So normally, where we would have E equals H times V, if we normally knew the energy required for a certain transition, instead of using that exact same energy, we're going to detune our laser beam. So I'm actually going to slightly reduce, so this was like the original frequency here. I'm going to intentionally detune it, or redshift it. Now, because of the Doppler effect, when the atom is moving towards the source of the photon, it blue shifts it, and as a result, the frequency then reaches the frequency that's necessary to create the energy that will bump, that the atom will absorb, and it will get the atom to the excited state, and then the electron will go ahead and drop down. That's Doppler cooling, in essence, because if the electron is going, or if the atom is going the other way, it's more redshift. So as a result, the wavelength gets even longer, and the atom won't absorb the photon. And if we do this repeatedly over many thousands of times, the atom will slow down and it will cool. And this is known as Doppler cooling. But Doppler cooling is, the problem with Doppler cooling, though, is it is not, even with Doppler cooling, you can still get it cooler. Like, it's still possible to get lower temperatures, which we want. So Doppler cooling is kind of your step 1. And then there's something called, okay, this is I think it's called Raman sideband cooling. This is sort of your phase 2 for cooling. And this is where I have to, really kind of drive this point into your, this might be kind of tricky to explain, but I think it's doable. I still have 15 minutes here, so bear with me. And don't worry, I know we're talking a lot about cooling, but trust me, like the principles you learn from cooling will greatly help you understand the other principles required for computation. So with Raman-Simon cooling, there's going to be, I want to sort of draw this diagram out for you. And it might not make sense in the very beginning, but you'll see why soon enough. This is sort of a harmonic potential, and this is our two-level system, right? So this is sort of the ground state, and this is the excited state. And I've drawn this tensor product. And if you know anything from a standard quantum computation, when you take the tensor product, so these are like sort of two different Hilbert spaces. Excuse me, wow. Excuse me. You take the two Hilbert spaces, and this gives you a new kind of energy landscape or a new configuration. So as a result, if this is inside of our atom, right, and this is this Hamiltonian, I'll have to explain very quickly, or this energy setup, because we have multiple ions kind of sitting in line with each other. These all have positive charges. You can kind of agree with me there. And as a result, they really don't want to, they really don't want to like get close together. In fact, there's kind of a distance here. Depending on which ion you use, it'll dictate the distance. And then we have our positive end caps here. But what you can also equivalently think of with these ions is you can think of like mass, like spheres, and they have springs between them. They have springs between them, like this nice little. And you can use Hooke's law and make a very nice classical approximation of this behavior, where as a result, they kind of sway back and forth, and they'll oscillate at certain modes of vibration. And those vibrations are quantized. They're known as phonons. If you're curious, it's a kind of quasi-particle. But the basic idea here is, this also gives us some vibrational energy levels, or external degrees of freedom versus your internal degrees of freedom. And as a result, we can kind of couple these together. And now our energy landscape kind of looks like this. So if this was your sort of first, so this would be like, we're in the ground state, and then we're vibrational state 0, ground state, excited state, and then vibrational state 1, ground state, so this is 0, wow. Ground state, but then this is 1, and then ground state, and then this is 1 as well, excited state, wow. Ground, excited, ground. So you see, but you also note that these energy levels are slowly going upwards. So this is the new energy levels we're dealing with here. I've intentionally omitted the other atomic energy levels here. But the basic idea is we have to factor in this quantized motion going on to achieve any further cooling. And there's something known as the Raman sort of sideband cooling. And this is particularly, it's not a very easy concept to understand, but the basic idea is you can kind of excite a photon to a certain level, and then using another photon, you can de-excite it. And you can excite, de-excite, excite, de-excite, and you can keep going until you reach your ground state here, in which case the temperature is now even cooler, which is super nice, because this also serves a double effect of one of the reasons we even need this cooling is to get the qubits into this ground state, something we can work with here. Raman-Simon cooling, I should tell you, is a kind of a form of optical pumping. And optical pumping is, if we can imagine this is sort of n equals 1 and n equals 2, and these sort of like hyperfine split energy levels. And I have a laser beam that can make this electron jump a whole energy level and then maybe one hyperfine level. So I can pump it up, and then it will spontaneously emit. So the electron will fall down an energy level, and I keep pumping, and eventually it reaches sort of this highest energy level, and it falls down to what would be Ket 0 or Ket 1, and then Ket 0 might be somewhere else. So I'm adding energy, I'm repeatedly adding energy until that electron gets to the state that I would like it to be. Now these Raman sideband is a little interesting because it deals a little bit with Raman transmissions, and I want to kind of bring that up very quickly. What we call a Raman. I hope I'm saying that right. If any of you guys have heard a different pronunciation, feel free to unmute, because I'm saying it like the Japanese food item, but I really don't want to make the mistake of
Raman.
Raman. Raman?
Yeah, Raman.
Raman. Okay, cool. Thank you. Thank you, Samarth. For those that don't know, Samarth is our president. So Raman. So it's a Raman transition. And the Raman transitions is very counterintuitive. In fact, that's why I wanted, like if I go all the way back up here, this is why I wanted you guys to keep this transition in mind. Like I told you a little white lie here, that the electron will not absorb the energy. In reality, that can actually happen, and that's where we get this sort of Raman transition. If you're more interested in this topic, you can look up Ramon Spectroscopy. And the basic idea is, let's imagine you have some kind of molecule. I'm making up ozone here, but it could be any molecule you desire. It's got some kind of bond. As a result, you have your normal atomic energy levels, but there's also some kind of vibration going on. Like it's not a stationary molecule, and within the bonds there's kind of so you have vibrational energy levels in there as well. So this could be like ground, some vibrational energy levels, and then maybe this is like a secondary standard energy level here, just another excited state. Normally, if I give it some radiation, the photon might want to jump to this excited state, and then it will jump, and then spontaneous emission dictates that it will jump down and it will release another photon with the same frequency and wavelength. And as a result, this is known as Rayleigh scattering. But there's also something else that can happen, which is you can have an excitation that happens, or you can have a phenomena. I'm going to draw this black box here, where I send in some energy, and then the resulting energy is of a different wavelength. So if this is sort of a wavelength 1, and then this is wavelength 2 that gets emitted from some kind of emission, we'll notice that wavelength 1 is not equal to wavelength 2 in this molecule. And that's the result of sort of this Raman transition, where you can actually reach what's called a virtual state or virtual energy level. It's kind of like this virtual energy. So what happens is your electron can actually reach this virtual energy state, and it can either go to a higher level, or it can actually decay to a lower level, a lower energy level. And so why is this virtual state permitted? Why is this even permitted? Well, we're going to have to go back to the Heisenberg uncertainty principle. There's this relation here, delta E is greater than h bar over 2. Basically, what this is telling you, this is a property of quantum mechanics. It's because it's the more common expression would be momentum and position. So it was like delta p, delta x. You might be familiar with this expression, but they both have the same idea, which is that if I know more about the position of my particle, I know less about the momentum. If I know more about the momentum, I know less about the position. So with this Raman transition, what this is telling us is if there's a lot of energy, if I know the specific energy, then I won't know the exact time. And if I know the exact time, I don't know the specific energy. So this kind of lets you get away with having these forbidden states, but it has to happen very briefly. Otherwise, nature kind of prohibits this. And this is, for those that are more, who want to be more rigorous, I encourage you to look up sort of the commutator relations. Which the commutator relations are basically, if you apply an operator to a quantum state, it will tell you whether or not one operator will influence what the other operator will measure, or if it will modify your quantum state in any way. So we can use that kind of Raman transition. We can stimulate that transition. So we can go to a virtual energy level, and we can just keep sort of pumping up and down and up and down and up and down until we get to ground zero. Although occasionally, because of the quantizations that are going on, there's kind of an auxiliary energy level we might need to use to pump up towards, and then it will naturally decay into the ground energy levels. That's sort of your Raman sideband. And I realized, like, wow, I only have like 5 minutes left. So if you guys are willing to stick around longer, please do. If not, this will be uploaded as soon as possible. But it's just because there's so much going on. But now with Raman sideband cooling and the Doppler cooling and the ion trapping, now I'm very happy to announce we're ready to do computation. We finally got these annoying, pesky little ions to behave properly inside of our trap here. These would just be our rods, and your ions are sitting in this nice single file line. So now this is where the difference kind of becomes very important here. I want to bring up that hyperfine structure, and this is just for the sakes, I believe this should be the terbium atom. Once again, I'm citing Christopher Monroe from his talk at Google. You can find that on YouTube. And also, I've been very sloppy here because of the hyperfine splitting. There are actually some other energy levels that are, but this would be S. This would be your S energy level, but it's split because of that hyperfine splitting. And this lowest energy level is Ket 0 or spin down, and this would be Ket 1 or spin up. So if let's say I want to be able to conduct some kind of, oh, and I should mention this is P, and then this stuff here is just kind of like a friendly little doodle that I drew just because it looked nice. I mentioned that in DiVincenzo's criteria, we need to have a qubit-specific measurement capability. So how is it that we can tell which state our qubit is in? How do we know? Is it in ket 0 or is it in ket 1? And this is where we start to talk about something called the cycling transition. And that's where the quantization becomes super handy. So if I give a certain frequency of light and the electron is sitting at this energy level at ket 0, what happens is it's just enough that it reaches this higher energy level, and then it will spontaneously emit another photon. So the photon goes out here. And that's how I know, like, oh, so I was in ket 0. But let's say I'm in ket 1. So let me redraw this. I'm not going to draw the other energy levels here. But let's say I'm in ket 1 now, so I'm slightly higher. If I give the same amount of energy, right, that electron will not, the transition won't even occur. It's not going to go to this sort of P energy level. It's going to stay or linger there, and there will be no photons. No photons get emitted. So because of this property, ion trapped qubits have remarkably high accuracies when it comes to reading out qubit states. And I'm going to draw this diagram here. This is something that gets shown very often. I want you to keep it just to give you an idea of it, like why this is crazy accurate. So this is the number of photons. This is the number of photons. And this is the probability of measuring a certain number of photons. So this is like 5, 10, 15, 20, 25, and that's the probability from 0 to exactly 1. So if I'm measuring, let's say my qubit is in ket 0, right? If I'm measuring in ket 0, it kind of looks like this is normally a discrete distribution. So you'd actually have like these little, it looked more like a bar graph here. So the probability of measuring 5, 10, 15, 20 photons follows this distribution. Whereas if I'm in ket 0, the probability of measuring 0 photons is pretty much near 1, or if I measure 1 photon because of background noise, it's pretty much near 0. So this is, and sometimes because of these, like you get photons versus no photons, sometimes in papers they'll call it the dark state versus the light state. And for those statisticians that are interested, both of these distributions follow a Poisson distribution, Poisson, excuse me, it's French. And as a result, I can draw this line here, and I can use this to discriminate between, okay, was the qubit in ket 0 or ket 1? Because I can, using these probabilities and the number of photons that I anticipate on detecting, I can discriminate very well with accuracies greater than 99% what the state was in with just a single measurement. But you'll realize there's always some kind of overlap, so you're never going to quite get 100%. But I remember in that talk was given, I think, 2015, the highest accuracy was 99.997%. And you want this high accuracy, especially when you're dealing with multiple qubits. All right, so that's your measurement. Now let's talk about your single qubit operations. And I realize I'm going over time here. So Mark, do you have any announcements you want to make? Because I still want to kind of go, but if you have any announcements, if you're free to give them now.
Oh, I was just gonna, if we had time, I was gonna show on AWS how the bracket circuit will look, but I'll just send the link in the chat. Sorry, on how the IonQ circuit will look. And then also, yeah, like the deadline for applying for working on the protein folding project and getting a stipend for doing so is February 1st. Sadly, it's only open to UC Davis and Sac State and Los Rios Community College students for now. But if we don't find the right folks, we will be looking to maybe look outside. And yeah, we'll definitely it'll be a GNU GPL project. It'll be open sourced, and it'll be on GitHub. So if anyone wants to collaborate on it and wants to maybe get their school involved, or a team of people, then yeah, please just get in touch with me. And I think it'll be a really, really fun project to see how we can use quantum computing to make protein folding more accurate.
All right, thank you so much, Samarth. Yeah, I mean, once again, I understand, like I'm stretching the time here, but it's just like there's a, I think I'll just need like an extra 5 or 10 minutes here, and then But for those that do need to go, this will be on our website, which is in chat, so you're free to access it there. But please do feel free to stick along. I do appreciate the company. Tom here asks, which of the two distributions is the one for 0 and 1? So the one that I doodled in here, I should probably like draw it like this. This here is the distribution for the Ket. This is Ket 0. No, Ket 1. Excuse me, the dark state. And this is for Ket 0. This is for Ket 0. And we're doing this on a ytterbium ion. Ytterbium ytterbium ion here. So this is so this distribution here would be for if it was in the excited state, and this distribution down here would be for the Ket zeros. And you notice it's kind of flattened out, but the probability of getting these other, a much larger number of ions is greatly or photons, excuse me, number of photons is greatly increased. And usually what happens is with the ion traps, there's kind of they'll have a camera. There's usually like a camera. So if I were to draw the trap again, I'll just draw like the arrangement, the 4 electrodes or rods you can think of. There's a camera kind of sitting here that will be able to catch the flashes. Usually it's not a true camera, it's a charge coupling device, a CCD. Oh yes, and Samarth has a repository with some examples for IonQ, which is the company that works specifically with ion trap based qubits. Now with Tom, does that answer your okay, cool, awesome, perfect. I was just asking if it answered Tom's question here. So now we can start to explain these single qubit operations, and this is where things start to get a little hairy. So I have, in the best interest of everyone here, I've omitted the Hamiltonians. If you really want to look at how this works, I encourage you to look up there are some lectures from MIT and other institutes about what we call quantum optics that will explain, or the Jane Cummings Hamiltonian, which is responsible for explaining some of this stuff. But I digress. So let's kind of redraw that model I was going with. So this is still ytterbium. It's a ytterbium 117. We've stripped away 1 electron, and we still have Ket 1 here and Ket 0 here. Awesome. So they're still chilling out here. And I want to mention something here. The gap between Ket 1 and Ket 0 is at the microwave frequency. It's roughly 12.6 gigahertz. Roughly 12.6 gigahertz. So there are 2 options you can have to create superpositions. So once again, superposition is just some combination of Ket 0 plus some combination of Ket 1. We can either use this fact, we can use some special microwave pulses to get into a superposition state, or a mixture of 0 and 1, or we do that stimulated Raman transition again. And then the Raman transition is actually the more preferable alternative, just because sometimes it gets really tricky dealing with these microwaves. So how that works is there are 2 laser beams with frequencies that have a gap of 12.6 gigahertz here, I think. Yeah, there's a frequency difference, and you have 2 laser beams that are kind of targeting this thing at the same time, 2 laser beams. And what happens here is this can actually, with these 2 laser beams, we can do that Raman transition. It's called the stimulated Raman. So this is another sort of virtual energy level. This doesn't actually exist, but we can actually coax these the electron to kind of go up to this energy level, and then we can use another beam to kind of bring it down if we wanted to a certain. So we can represent this mixture here. So these you'd have these lasers here, and that could give you that stimulated Raman transition. And this happens in that example I gave with a Raman spectrometry, where you have an electron that can get excited into this virtual energy state, but it can't last there forever. And as a result, it will decay into a quantized energy level. But inside this virtual energy state is where you get your superposition. That's how we can, get the alpha, alpha and beta. And you can actually express any kind of rotation you're interested in using those kind of laser beams. And in fact, you do something with what's called sort of the Raman beat note. Raman beat. And usually what beats come from the fact that when you combine 2 different frequencies, so this was like F1 and maybe F2 at a slightly different, you're going to see something like, oh, let's see if I can doodle this. So it looks like there's kind of an underlying frequency that's going on inside there. And this Raman beat note is kind of responsible for how you can tune your stimulated Raman transition. So basically, we have the phase and the, let's see if I have it here. It's the phase and the time of application, or the length of the beats are responsible for being able to manipulate your superposition state. This is how you would do it. And I'm going over a lot of detail, mind you. Like I've really skimped over some of the more technical nuances, but but basically you do have, this is how we can create that superposition. Now the final element is how do we couple, how do we get 2 qubits to, how do we get a gate that interacts with 2 qubits? And I want to bring your attention to the Craik-Zoller gate. This is proposed in '95 by the authors with the same the last names that I am presenting here. And Craik-Zoller is how you can get these 2 ions to play nice together. And I should mention, by the way, when we are using those lasers on the ion here, because of the Coulomb forces, there's repulsion here. It's actually easy. You can actually target individual, you can physically target individual ions because there's an actual like visible distance between these. So that's how you would do the single qubit. The Craik-Zoller gate or Craik-Zoller implementation is how you can couple 2 movements. And Craik-Zoller implements a CNOT. There's also something called the Molmer-Sorensen gate, which I believe is a controlled phase gate. And there's also something called the Ising XX gate. That's also another implementation. But Craik-Zoller was, in terms of explanation, the easiest one I could find. So once again, I want you to remember that these ions have a coupling between them. They're kind of rocking to and fro, and they're quantized, by the way. So they have these vibrational modes that are quantized. As a result, once again, I mentioned that we took that tensor product between the vibrational modes, the external degrees of freedom, so the atoms moving, versus the internal degrees of freedom, which are the energy levels that are restricted to each ion. And as a result, our energy levels are kind of interspersed. So you can have something that looks like this. And this might be caused by the vibrational energy, and this might be the ground state in your atom, and this might be the excited state, ground state in the excited state. So now we want to implement a controlled NOT gate. So what does a controlled NOT gate do? Well, it does something that looks a little bit like this. 1, 0, and then this is 1, 1. So if I have 2 qubits and they're in ket 0 or this is the first qubit, usually you have what we call the controlling qubit and your target qubit. If the control qubit is 0, nothing happens. So nothing really happens here. This would be 0, 1, everything's safe. But if this is this is a 1 here, what happens is this becomes a 1, 1 because it's targeted, and this would become 1, 1, 0, I believe is what happens here. This might not be, I hope this is the correct table that I have here. But basically, even if this isn't, or a controlled NOT should be this one, 1, 0, there you go. Or you can express it more succinctly as, if given x, y, x, and then you take the XOR, basically, that should be a more succinct representation of what's going on. But with the Craik-Zoller gate, let's imagine we have 2 qubits, right? The 2 qubits are basically the Coulombic force acts as a data bus between the qubits. So I have, both these qubits have that vibrational energy level. And let's say that the control qubit is now in the excited state, but this qubit is not in the excited state. So it's just kind of sitting here, ket 0 and ket 1. So I go ahead and check, and I'm like, oh wow, okay, this qubit is in the excited. So now I have to find a way to bump 0 into 1. I got to find a way to get this to bump into 1. So I can actually use a laser to de-excite this electron down to this vibrational energy level. So note it's not ground state. It's just that vibrational energy level. And as a result, let me think here. What did I? Okay. Or I transfer the energy. I shouldn't say. I transfer the energy to the vibrational energy, which actually brings this electron up. It brings this electron up here. So I've taken the energy that was at this sort of level, and using some laser setup, you can actually transfer it down to this vibrational energy level. And as a result, that means that if anything's in ket 0, it's now sort of promoted to this vibrational energy. But now I apply I apply some energy, and notice that this energy level is not equal to the energy level, or this energy is not equal to the difference in energy between the actual ground in the ion and the actual excited state. It's only between the vibrational state and the excited state. So as a result, I apply this energy, and now it goes up. So now by monitoring this one qubit, I can now tell it's like, okay, it's in state 1. I can kind of get it down, or I can demote it to this vibrational energy level. And by transferring that energy, because you have to remember that these ions are all kind of coupled together, that energy kind of make its way, or it'll oscillate to the other qubits, and it'll promote this electron to this vibrational state. And then with a little more energy, it gets bumped up to 1 essentially. So that's the Sirac-Zoller gate there. Molnar-Sorensen uses like a different phase-based system, but this is like the easiest. It has a very nice explanation, and I think I got this off of Christoph Wunderlich. He gave some very nice. I'm trying to remember. I think it's at the ICMP. It's like the International Center for something physics. But he gives this explanation, so I'm just sort of bringing it to you in the context of everything else. So I've given you a single qubit operation. I've shown you how to do an operation in which you can get pairs of qubits to work together. And I've also proven we can have very clear readouts, and all these other properties, especially this cooling and being able to get to that fiduciary state. And the fiduciary state, after a computation, if you still have qubits that are in other odd energy levels, you can use optical pumping, this thing that I mentioned here. So just add more energy at these quantized levels, you keep bumping it upwards, and eventually it reaches a point where it'll fall back down. And when it reaches like this ket 0, you add the same amount of energy, it won't move anywhere, because the other energy levels are so far away that it just won't, so you essentially reset the circuit. You reset your qubits to ket 0 using optical pumping. So that satisfies pretty much all 5 criteria of the DiVincenzo's thing, because I mentioned you can have, we have multiple ions going on here. We can, make the single qubits, and we can have, put them in this initial state. But before I end today's workshop, and I understand I've really gone over time, the scalability is a problem here, because we need to be able to know or have some knowledge of these quantized modes, these quantized so that's not the right, excuse me, that's not the right diagram. These vibrational modes. Every time you add another ion, this gets a lot more difficult to work with, these kind of phonon configurations. So as a result, one of the ideas that's going on, or I think there are 2 different ideas for how this might work, is you can have multiple ion traps. And you can have a system of fiber optics, and there's like a kind of multiplexing unit here that will allow different traps to interact with each other. So you can kind of shuttle, the more ambitious one that I've seen is you have multiple traps, and there's a specialized channel or magnetic funneling system where you literally move the ions around between different traps. And this lets you have more ions, and you can scale up to hundreds or thousands. That's kind of the dream goal here. If you're I think the device is called a QCCD, if you're interested. But that is in essence the basic principles behind your friendly ion trapped qubit. Are there any questions before I decide to go ahead and end the recording and call it a day? I appreciate your patience once again. Usually I can keep these things within 60 minutes, but just because there's so much going on, and it's something I'm really into, I wanted to kind of give a more thorough explanation.
So I just had one question. So if you're like comparing this particular implementation to other ones like superconducting qubits, or what's another? I think there's like optical, like in general, like where do you think like ion trap shines in comparison to the other implementations?
I think the main things that or at least I'm a huge fan of, I haven't done as much in terms of like comparative work, but that is an excellent question, is that ion traps have really nice sort of long-lived lifespans. And you mentioned photonic qubits, that's very much a thing, or even Gaussian boson sampling. But the problem with photonic computation is it's really hard to get light to interact with actual matter, which you do need for certain operations. as well as I think I've heard like scaling issues as well. There's such thing as linear optical quantum computing, LOQC. LOQC has some, from what I last read, and this might be inaccurate, LOQC has some scalability issues because with every new qubit you introduce, the rate of hardware you have to add grows exponentially, which is not good. That's the very thing we're actually trying to deter. So I think the lifespans for ion trapping and I would have to say that these are also some promising technologies here. This QCCD as well as the photons here. But the huge selling point for ion traps was they're very stable. They're just incredibly stable. Very long-lived. Those are kind of your main selling points, I would have to say. Whereas you mentioned superconducting, that's easier to contrast because superconducting qubits have incredibly short, relative to ion traps, they have incredibly short lifetimes. In fact, but then again, the reason why, when I was mentioning DiVincenzo's criteria, so if I go back up here, the reason why I mentioned, okay, so the decoherence issue should be relative to the qubit lifetime versus the gate times, not just the length of time it takes, is because even with the superconducting qubits, the gates are pretty fast. So as a result, you can still do a lot of useful computation. In fact, I'd even argue the silicon superconducting qubits are easier to fabricate. You can use a lot of existing technology to fabricate these silicon qubits, which is why IBM and a lot of other companies like to go for those superconducting qubits versus ion trapping. And ion trapping has that scaling, the trickiness with scaling, where you might have to use some kind of exotic fiber optic setup or maybe some kind of microchannel or some electromagnetic funneling system to shuttle your ions back and forth. I hope that's a decent explanation.
Yeah, no, that was really good. Thank you.
Yeah, no problem. Any more questions?
If anyone doesn't, sorry, could I just say one more thing?
Yeah, go ahead. Absolutely.
So if we're comparing, or not comparing, but like you said, one of the key points, or I guess aspects of ion trap that's really nice is the long decoherence times, but relatively, don't they also have longer gate times? So it's sort of
excellent. So you do point out there is a so these are at 2 a.m. Oh wow, okay. So sorry, I'm reading something in chat here. Tom says, "Oh, awesome, undergrad in CS. That is excellent to hear." I mean, I'm also an undergrad in CS, so we're both in the same boat here, Tom. But yeah, I'm glad to hear that the recordings will help. So, sorry, is your name Samyak? Am I pronouncing that properly?
Yeah, that's right. That's right.
Okay, cool, awesome. So let's see. You were asking. Oh, I just lost my. Could you repeat your question? I'm terribly sorry.
Yeah, sorry. It was about the long gate times.
Oh, yes. Okay. So you also mentioned, and that you're not wrong. In ion traps, the gates do take a decent amount of time to do, but what was I thinking of here? One of the other selling points for ion traps is they're not. I believe this is true. I have to do some more verification on my end. Is that they're not as susceptible to external electromagnetic interference. In fact, with the hyperfine system, there's actually a very nice property that most research papers will cite to you, which is that they actually have some resistance to external, spurious magnetic fields. Whereas with a superconducting system, like you might have your transmon qubit. Things can get kind of hairy. They're very, usually you have to put this thing in a Faraday cage or something to prevent external, leakage or unwanted frequencies. So I would argue that's your other selling point. Although you do make a good point that yes, I don't know, I'm not certain, at least from my knowledge, that the ion traps take longer, but I am aware that some operations do take a decent amount of time to sort of hammer right in those ion trap systems.
All right, got you. Thank you.
Oh, those are excellent questions. Thank you so much. See any more? Let's see, any more questions? I'll give it one more minute, and then I guess I'll go ahead and call it wraps because I realized wow, definitely went on for a bit.
Not a question just for you, but just generally, what are everyone's thoughts on the 4 million quantum volume of IonQ versus the quantum volumes of 128, I think, is where IBM is at, and it's the next highest quantum volume. I know that some people just say quantum volume, they just show that quantum volume was not a good measurement, and then other people said that like, oh, it was really good, and actually like IonQ is just a really like just doing a really good job.
I don't think anyone else here has a. I mean, we can actually. Oh wow, okay, Tom's in Germany. Wow, awesome. What was I thinking? I think they would just. Yeah, I'll briefly kind of splurge on this. Maybe I'll go ahead and stop the recording here just to keep the workshop thing going. So I will go ahead and